Here we have a section of a lecture on acid-base chemistry. This section in particular deals with calculations involving pH and pOH. Thus, I want to explain to you what pH actually is and how it can be calculated. First, what does pH stand for? Well, pH stands for power or potential of hydrogen, referring specifically to a proton as represented by H+. Just as a brief aside, we know that hydrogen, specifically the hydrogen 1 isotope, also known as protium, is composed of one proton and one electron. This is an important distinction as any other isotope of hydrogen, such as hydrogen 2, also known as deuterium, would contain one proton and one neutron in this case, or more neutrons depending on the isotope, in the nucleus, as well as one electron. Now, recall that protons and neutrons comprise the nucleus of an atom, while electrons are moving in electron orbitals around the nucleus of an atom, and therefore have much more freedom of movement. Therefore, a hydrogen 1 atom that has lost an electron means that the resultant atom now consists of one proton and 0 electrons. For this reason, it is common to represent protons as simply H+, signifying hydrogen without an electron, aka 1 proton. Using the Bronson-Lowry definition of an acid and a base, acids are species that can donate a proton, while bases are those that can accept a proton. A common base is the hydroxide ion OH-. For this reason, we can quantify the acidity or basicity of a solution by using pH or pOH, which are essentially measures of the concentrations of protons or hydroxide ions in solutions, respectively. To understand where these metrics come from, this brings us to the second point shown here. As stated, the concentration of protons and hydroxide ions shown here, remember that brackets around a molecule indicates concentration, are very small, so these concentrations are transformed using the logarithmic function to make it more intuitive. In particular, here we see the formula for pH and pOH, which are both the same using either the concentrations of protons or the concentration of hydroxide ions, respectively. From here, I will only look at the concentration of protons, as again the formulas are the same. As shown, pH is equal to the negative log of the concentration of protons in a solution. You may know that the pH of pure water is equal to 7, so I use that here to show you this formula in action. Pure water at 25 degrees Celsius has equivalent proton and hydroxide ion concentration, being equal to 1.0 times 10 to the negative 7 moles per liter. Putting this value into our pOH or pOH formula provides an output of 7. So how does this value come about? Well, this requires some understanding of the log function. Remember that log is essentially the opposite of an exponent. Otherwise stated, this function finds what power a given value would need to be raised to in order to obtain a specified outcome. This is shown visually here. Here we have a value a raised to some power y is equal to another value x. As seen on the left, a log function will tell us what value y needs to be to obtain x if the value a is raised to that power. For example, if we have 2 raised to the third power, that is 2 times 2 times 2, that of course equals 8. In this case, we know that 2 cubed is equal to 8. If instead we were given the output 8, and we wanted to know what power we would need to raise 2 by in order to get 8, we would use the log function. The log function essentially would take 2 and look at the output 8 and provide us with the value 3, meaning we have to raise 2 to the third power to obtain 8. In the case mentioned prior, we have a base of the log function equal to 2, meaning 2 is being raised to some value to obtain an outcome of interest. By default, however, log has a base of 10. This means that the log function will tell us what power we need to raise 10 to in order to obtain an outcome of interest. This is very useful when dealing with very small fractions, as is in this case with the concentration of protons and hydroxide ions. Think, for example, that I mentioned prior, the concentration of protons and hydroxide in pure water is equal to 10 to the negative 7. If we ponder this, This means that the concentration is 0.00000001 molarity, or 1/10,000th mole per liter. This is not very clear to most people, so the log function becomes useful here. We know from scientific notation that raising 10 to a power will either multiply or divide that number by 10. If the exponent is positive, the number will be some multiple of 10. If the exponent is negative, on the other hand, the number will be the reciprocal or 1 over some multiple of 10. In the case of proton concentration, the lower the exponent value signifies a greater concentration, as this means the number is closer to 1. For example, 10 to the negative 3 is 1 over 1,000, while 10 to the negative 7 is 1 over 10 million. To account for the fact that all exponents will be negative due to the concentrations being less than 1 molarity, a negative sign is placed in front of the log function to make whatever outcome we have positive. This also means that there is an inverse relationship between pH and proton concentration. Otherwise stated, lower pH values indicate greater proton concentration, and higher pH values indicate lower proton concentration. Now that we have an understanding of pH, let's see this in action. For a very simplified example, let's say we have a solution where the proton concentration is equal to 1.0 times 10 to the negative 3. Using this, we can plug in this value into our formula and see that the pH of the solution is equal to the negative log base 10 of 1.0 times 10 to the negative 3. If we divide both sides of this by negative 1, we get the negative pH value is equal to the log base 10 of 1 times 10 to the negative 3. Now, using the relationship stated prior, we know that this means 10 has to be raised to some number to obtain a value equal to 1 times 10 to the negative 3. We can interchange an unknown value y for our unknown pH as shown here. Again, this leaves the final question of what power must we raise 10 to in order to obtain a value of 1.0 times 10 to the negative 3, or 0.001. Logically, this means that the missing value y, or pH in this case, should be equal to 3. This of course means that pH in this case is equal to 3. Lastly, the proton or hydroxide concentrations can be found in a solution from the pH or pOH values respectively if these values are known. This is essentially just the opposite process that we conducted prior. Namely, 10 raised to the negative pH or 10 raised to the negative pOH values will provide an output equal to the proton or hydroxide ion concentration, respectively. And finally, here we have a pH scale that is commonly known. Here we see again that the lower pH values indicate greater acidity, as this represents a larger magnitude proton concentration, while higher pH values decrease acidity as proton concentration diminishes.